Students, and welcome to this other edition of our Numerical Method 2 class. I hope you enjoyed the test yesterday, the online test, which was a quiz. I hope you did well. And I wish you all the best for today's class.
Okay, so say I have a question.
Yes, you can ask your question, please.
For the comprehensive test that we're going to write, is it covering all the chapters or only selected chapters?
Okay, a comprehensive test. It will be like a global test, like global, right? Because it's comprehensive, but it will be mainly based on the last part. Mainly, when I say mainly, it means that about 50% or over 50% will be based on the last part. That is from numerical integration. No, not exactly. That would be mainly, yeah, because that numerical integration is is this second chapter. And what we are going to start today about the eigenvalues and eigenvector. So it will be mainly that last part. We have 2 weeks for that because we still have this week, because the comprehensive test, if I don't know if you have the dates already. I think it should be on the 12th of November.
Yes, it's 12th of November.
Good. So it's more than 2 weeks because we still have this week, right? And then from next month, we have 12 days. So it's over 2 weeks. So we still have this week because I will introduce the chapter 3 today, or the notion of eigenvalues and eigenvector today. And then for the rest of the week, that's what we'll be doing. And next week, similarly, we'll cover, and the following week, we will do more practical. And I think that should be enough. And I will go directly through the main important concept. I will not be going through all the slides. Because you have the slide, you can read, right? I will just introduce, explain, and then we go straight to the core of the matter. What is important, what you should expect, things like that. Because you have the notes. You're not writing down the notes. So everybody, you already have the note, you can read the note. Oh, but I have to upload it anyway. I will upload it after the class. I will upload chapter 3. But some of you already even have, because they are the same notes. So yeah, I hope I've answered your question, or you want more clarification. Are you satisfied with the answer, or you want more clarification?
Yes, I'm satisfied with the answer.
Okay, so we mainly on the last part, mainly on eigenvalue, eigenvector, mainly. But there will be a bit of numerical integration. That is it. Now, for those who will be writing the makeup test, that one will cover the entire program. Okay, so today we are going to start with eigenvalues and eigenvector. I will quickly share the slide. And this is the very last chapter. If you look, the number of slides, there are a total of 24 slides. as I already said, I will not go through all the slides because you can all read, but I will only focus on the main concepts. Okay. Let's start with the concept of eigenvalues and eigenvector. What are they important? In fact, most of the concepts that we encounter in numerical methods were designed in order to solve real-life problems. If I take a simple case in engineering, currently I'm sitting in a building. You too, you're somewhere in a building. If not in a building, maybe in a car, in a structure. I mentioned building. A building is a structure, a car is a structure. Yeah, but the difference with the car is that it's moving. So when you talk about structure in general, structure is static. But a car, when it's moving, obviously it has a structure because when the car is fixed, right? Or is when the car is not in motion, right? In an equilibrium state, you talk about a structure. That is the shell of the car. All that, what makes the car to be strong and can be able to carry people, can be able to withstand accident, things like that. That's the structure of the car. The chassis and the shell. That's the structure, similarly to the house. Okay. And you also know the pendulum. Harmonic oscillator in physics. You did that in high school anyway, or even in differential equation. When you write the second order differential equation that will model the oscillation of an harmonic oscillator. Let me open another slide to explain this. Instead of using a radio or Okay, so eigenvalues and eigenvector. And this already you encountered this in linear algebra. So it's not something new. So the only thing that is new is the numerical computations. Okay, now when we talk about, okay, so I was talking about the structure. I will just take that case, the case of a structure. Okay, now if you want to study the stability of a structure, remember that if you build a house, you are not sure that that house will withstand the test of time. It will withstand winds. I mean, natural phenomenon, right? A phenomena. If you are not sure, that is, if there's a slight perturbation, right? When I say perturbation, that perturbation might be what? It might be a storm, because we have storm in nature. It might be a strong wind, something. It might be, I don't know, maybe an earthquake. I mean, maybe not at a higher magnitude, but that is a perturbation. If a slight perturbation can collapse the structure, there's no need of building that structure. So one of the application of eigenvalues and eigenvector is in the study of stability of structures. Your harmonic oscillator, anything that can be a structure, a system in general. That's where you can. Okay, also in the solution of differential equations. Remember when you have a linear differential equation and you write the general solution of the system, you usually write the solution of a differential equation in the following form. If, for instance, you have a differential equation in y, the solution will be y, let's say yt or yx, let's say yt, right? And in general, depending on which type of the order of your differential equation, it will be something of this form, where you have the sum of an expression of this form, sum of I, of course, and then a certain vi. Roughly speaking, the solution will be something of this form. Right. Okay, so that is if you have a scalar equation. So this is like general solution of a scalar equation. When I say scalar differential equation, I mean here by linear differential equation. Right. Now, if you have a system, the solution will be of a similar form. But now this time, you have exponential any way there will be no summation there, but wait, what am I writing? Yeah, it's something like this. Yeah, I think what I wrote there is everything has been done because I wanted to write with the exponential of a matrix like that, and then you have a vector times a certain initial vector here. But all this, when you multiply, it gives rise to this one. So this is a vector. In fact, not necessarily even for system, right? Not necessarily scalar and system. Scalar and system. Right. Anyway, revise your numerical class. Okay, now what I want to show here is that this lambda are the eigenvalues of this matrix. Because what you do here, you diagonalize this A, the matrix A. You diagonalize this, right, this one. Then you have the diagonal matrix, and then P inverse, right? Now, if you want to compute the exponential of this, so if you diagonalize this, then exponential of the matrix, of course, that you multiply by a certain t, and you multiply there, will be P exponential of that matrix, this one, P inverse. That you know this from linear algebra. Now, when you write your solution of this form, you agree with me. Okay, now D here is there. It's a diagonal matrix, and the element of the diagonals are the lambda i's. So you see that if you expand this now, this will be that invertible matrix, and here you have exponential lambda 1t up to exponential lambda nt. And you have P inverse here. So you agree with me that when you expand this, when you will expand this, this will give you this is symmetric because this is symmetric, this is symmetric. But when you multiply by a vector here, similarly, this is a vector. Anyway, this is not important. This is a vector. It will give you something of this form. Right, it will give you something of this. You see, so it's not a magic. Obviously, for linear system also, when you use a characteristic equation, right? When you use a characteristic equation, it is almost similar. It's also of this form. Right. So that's what I wanted you to see. Now you can see that these lambdas are the eigenvalues of what? Of A. You see. You can also study the stability of the solution of the differential equation through this. If all the lambdas are negative, then the solution of the system that this that the system, the differential equation models, is stable, right? So this is just to put you in real life situations so that everything will not appear to you like just theory, just theory, just theory. These things have application in engineering. Just that we don't have engineering classes where you can see that, oh, actually, this is where you apply this thing. Okay, so that's for the introduction. At least I took this example to motivate and show you that it is very important. Now, coming back to this, if you want to get this, the eigenvalues of A, it's obvious that if A has a small size, you easily compute the eigenvalues and eigenvector. But now, if the matrix A is very large, how are you going to compute the eigenvalues and eigenvector? You need a computer. And in real life situation, engineers, when they model the system, the matrix, that matrix A, the size of A is generally million by million, if not hundreds of thousands times hundreds of thousands, or thousand times thousand. So the number of entries is already in the order of the million. You see, meaning that in order to approximate this, we need to develop powerful algorithm. That's why there are many methods. You start with a simpler method for you to gain insight, understanding, and later on, because of some drawbacks or some peculiarity of related to the properties of the matrix, right? Then there are new and more powerful methods that are adopted. So roughly in science, that's the direction. Start with something simple that can give you an idea, okay, this is how we can proceed to solve, but maybe it's not robust, it's not scalable or strong enough. Then you move to a better algorithm that will give you more robust, realistic solution. So roughly speaking, that's the idea. Okay, this being said, I can now dive into the methods. The simplest method, the very first method, when it comes to the computations or the approximation of eigenvalues in eigenvectors, is the method called the power method. The power method. So that's what we are going to cover. I hope this introduction has really set the stage for you, your understanding of the subsequent development. Okay, now in terms of the power method, the power method will give you what you call the dominant eigenvalue. The power method in general does not allow you to get all the eigenvalues. It's just the dominant. Dominant here means dominant in terms of absolute value. If you take the absolute value or the magnitude of all the eigenvalues, the one with the largest magnitude is what we call the dominant eigenvalue. It can be positive, it can be negative, provided the absolute value is the largest. For instance, if I have these eigenvalues, let's say I have lambda 1, or I will be compelled to write here, otherwise I'll have to switch back to the previous slide, which is time consuming. So I'll write it here. So say for instance we have 3 eigenvalues, lambda 1. Oh, I will know. Okay, let me take the subscript on top. Let's say that lambda 1 here is -1. Another one, lambda 2, is -10. And then lambda 3 is 8. If I ask you here, what is lambda 1? I mean, what is the dominant eigenvalue among these 3? What will you say? Janice, any clue?
Say, is it 8?
You see, that's why I purposely gave this example and I asked you. And it's good to answer because you answer sincerely. And then next time you will not make the mistake because you will understand the concept. Because if I just spoke as I did and continue, you have the impression that you understand. That's why I gave this example to make sure that you understand what it is. Okay, now you say 8 because for you 8 is the largest, right? Now, if I look at the magnitude, if I look at the magnitude of each one now, what do you have? The magnitude, let me take the first one, the magnitude of lambda 1 is 1. The magnitude of lambda 2 is 10. And the magnitude of lambda 3 is 8. So this is the dominant. I mean, when I say this is the dominant, not this one, but lambda 2. So if you are asked at this stage, what is the dominant? Now, if I write down, I will say, this is how I write it. Isn't it? This is how I write it, no? Because the largest is absolute value of lambda 2 is greater than absolute value of lambda 3, and that is greater than absolute value of lambda 1. So the dominant is this one, the first one, this one, lambda, the modulo of lambda 2. Therefore, this is the dominant eigenvalue. And this is what the power method will compute. The power method will compute lambda 2. Is that clear now? Is it clear? Is that clear, or I should repeat? If you don't understand, because this is still...
It's clear, sir. It's clear.
It's clear. Yes, Sandile, what did you say, Sandile? Sindile, sorry. Sindile.
It's clear. Say it's clear.
It's clear. Great. Okay, great. So we can let me erase all this. Okay. So that's the power method. That's what it will compute. Now that you understand what it will do, now how do we perform the power method? Okay, the explanation I given here, I will not go into all the details because you can read, and please go through, read, and if you don't understand, ask the question. Otherwise, it will take more time to go through the slide. Okay, so I will come here. This formula that allows us to compute lambda 1, which is the dominant. If you look at this one, you can see we did exactly, we call lambda 1 the dominant, right? Because in absolute value, lambda 1 is greater than all the remaining eigenvalues. So lambda 1 will be our dominant eigenvalue. And you are familiar to linear algebra, huh? This is linear algebra. All this is linear algebra, right? It comes from the fact that if lambda is an eigenvalue of A, lambda j, and uj is an eigenvector, this is the relationship between the two. right? If I apply A to an eigenvector, it will be proportional to the eigenvector. And the constant of proportionality is your eigenvalue. So in other words, the eigenvalue tells you whether by applying A in a certain direction, right? Because we call that the principal axis. If you apply, because A is a matrix, it represents a linear operator. So when you apply it, it might magnify or it might shrink the vector in that particular direction, right? That is the geometric interpretation of eigenvalue. So is that constant of multiplicity? I mean, the constant of multiplicity, no, I mean, the constant of proportionality, right? Lambda, the constant of proportionality, because this is proportional to, that is A uj is proportional to uj. And the constant of proportionality, lambda j, is what we call the eigenvalue. So I say geometrically it represents the magnitude, because in the space, when you perform that, in a particular direction, there will be a direction in which that will happen, and that direction is called the principal direction. And the axes in that direction are called the principal axis. So in that direction, the vector A, the vector U, will be magnified or shrink. Right. It's as if we have something like this. Let's say I have this, right? This is a body in the space. Now I perform a transformation on this, a linear transformation. Okay, now it might happen that in a certain direction, maybe in this direction, when I will perform the transformation on that ball or whatsoever it represents, you might have something like this. You see that in that direction, it is shrink. You see, it takes that, it pulls it in a certain direction, right? Or it might compress it. So maybe that's not the best explanation, but you have an idea of what I'm trying to say. All right, so that is to bring maths alive, for you to understand that those things are not just theory. Yeah, my colleague, when they started this thing, it was just theory. But later on, I don't know how to explain that. Later on, scientists understood, because mathematicians are like, they are the thinkers, they are the brain. God speaks to mathematicians through intuition, because he created the universe, he put the laws and everything there. Now he inspired mathematicians to write theories and all those things that describe nature. They might not see it directly, but in some branches of science, they will finally pick, oh, this thing that the mathematician, this is the application of physicists. They will understand that this is the meaning of this concept in physics, in real life. This is what it means. Mathematicians in the beginning, when they just do maths. So they communicate. Not that they have a particular relationship with God. I'm not saying that. But because God wants man to solve problems, he will just put in the intuition of man, because he's the one who gave us knowledge, intelligence, intuition, understandings of concept. So he put it there. And mathematics is that language or that science that describes nature. Mathematics is just that, right? You can write or you can describe any branch of science using mathematics. So that's the connection. I'm trying to show you that most of the things that you do in mathematics have an application in real life. But mathematician in the beginning, when he came up with the theory, they were just doing mathematics. But it came where? It comes from the brain. Are they the one who created their brain? No. Are they so intelligent on their own? No. So that's the only thing I wanted you to understand. So this is the linear algebra I was talking about. Now, when you take this When you take this, right? You take a vector now, you write it in, because that vector is in a space, right? Now, if you are in an n-dimensional space, you know that in an n-dimensional space, a vector can be written as a linear combination of the element of the basis. So if the dimension of the space is n, then you will find n linear independent vectors in by which any vector can be written as a linear combination of, right? So that is exactly what we have here. So if I take x0, an arbitrary vector in Rn or Cn, what you have here, you can write it this way, right? In Cn, because Cn is a vector or linear vector space of dimension n. You can write it this way, right? And therefore, if these are eigenvectors, right? You end up with something of this form, right? And this is where okay, actually, what I wanted to express is this one. But at this stage, if you look at this definition here, this can be written in this particular form. So the sequence, you can see that now through this we construct a sequence, and you have a raised to the power of k. That's where the name of power method comes from. It comes from this notation, power, because we have the powers of the matrix, a to the k. Right. That is where the terminology power method stems from. So this is mainly linear algebra. That's what I said. I don't want really to spend that much time there. If you read, it's really explained in detail. So by performing now, applying the A and using this formula 3-2 about eigenvalues and eigenvector, we come up with this relationship. And now you can see that when we factor, we have this lambda 1 to the n, because lambda 1, remember, is the dominant, right? Because it's the dominant, it means that in absolute value, we have this condition, equation 3-1, this. Now, if I divide everything by lambda 1, you see that the ratio will be less than 1. So that's why this, all the lambda divided by lambda 1 will be less than 1. So raised to the power of k will convert to 0. This is what we call geometric sequence, right? Now you see that if I take this now, knowing that all this will converge to 0, all this will converge to 0, I can rewrite this 3,9 in this form, where epsilon k goes to 0, and that epsilon k, in fact, represents this part. It represents this. Okay. Good. And then we use an arbitrary linear mapping. We apply, because it's linear, you get this, right? And knowing that this will converge to 0 because of the linear mapping, right? Now, if you take the ratio, this ratio, because remember that this is lambda to the lambda 1, this is lambda 1. So so this is 1. Lambda 1. This one. Okay. Now, if I write this phi of phi of x to the k plus 1 from this, right? Similarly to this, will be lambda 1 to the k plus 1, right, into the same thing inside here to the 1, but the difference will be here. This will be epsilon k plus 1 to the k plus 1 like this, plus 1. Now, if I take the ratio of the two, if I take this and I divide by that, the ratio, right, this one, since it's k plus 1, I will just put k plus 1. Sorry. To simplify the notation, I will put k plus 1 here instead of putting of that, and I divide by this one, and this one I call it phi of it to the k to denote this part. Now, if I divide, you can see, you agree with me that this will be divided by this. So I will have lambda 1 to the k plus 1 divided by lambda 1 to the k, which is lambda 1. Just this is the factor. So here I have lambda 1. Right? Now for the inside, the inside part, the inner part, I will have a ratio of the form I will have this ratio. This one is exactly the same. You can see that here we have the phi 1, which is phi 1 actually, like this, right? Plus this one, plus this error term. Okay, I will just k plus 1 like that, divided by, you can see this one, the same expression. That's exactly the same expression. This one, u1, because you can see that we still have u1 there and u1 here. It doesn't depend on k, so it remains the same. Okay, anyway, and that expression, this expression, you put it there. Now, you agree with me that if I take the limit of this ratio, which is written here, we call it rk. So this is our rk. So you agree with me that if I take the limit of that ratio, right? You take the limit of that ratio, this will cancel out, right? This will cancel out. First, this will go to 0. This part will go to 0, right? I'm talking about this one. This part, this one will go to 0. Remember that we have it here. I wrote it here. That this converges to 0, right? Be it with epsilon to the k of k plus 1 in the numerator and k here in the denominator. So the ratio, this ratio will converge towards phi u1 by phi u1, which is 1. So if you take the limit, finally it will convert to lambda 1. So that is it. That's how we should understand all the explanation there. So I wrote the details of how you do that. So I repeat that the factor of lambda 1, this factor, this ratio of this divided by all this, I cannot write it down because of the, okay, let me see. Okay. Here is u1 plus phi. Now this is epsilon to the k, but this is k plus 1. Now if I take the limit, this will go to 0, this will go to 0. So this factor will go to phi u1 to phi u1, which is 1. So it will convert to 1. And this entire factor, when I take the limit, it will convert to lambda 1. And that's what we have here. So in other words, from this, now we can derive our power method from this ratio. So Here we just say linear mapping. Phi is a linear mapping, right? It's a linear mapping. We didn't say which linear mapping it is. Any linear mapping will do the job. Any linear mapping will do the job. Okay, now in the power method, that is exactly what we do. You can see, you can look at the algorithm, but for now it's not important. Let us go straight to the application. How we'll apply this? I will explain it. How we'll apply this concept here. We'll apply to this example. Please, I want to make a remark, a caveat, a warning. The power method as introduced here is a variant of the power method as introduced in other textbooks. But I will come back to that second version of the power method as introduced in other textbooks. It's good to give both so that if you encounter the other one, it will not look strange to you. So I will do both. But the second power method will be mainly introduced when we'll be talking about the shifted power method or shifted inverse power method. But for now, for the purpose of simplification and also for a better mathematical description as we did, this approach is more elaborated as we did through linear algebra, the way we proceeded. Now let us look at this particular example and we will see how we apply either this, in fact, power method, this, the way it is explained here, is exactly this procedure, this one. That's exactly what it is. This algorithm, perform, right? This algorithm perform this equation 312. All this computationally, this is how you perform the algorithm. And that's what we are going to do now through this example. Obviously, you have the modified version, but for now, it's not. You can read that. Now, we want to see how to apply this. Power method, if you remember, we said we construct a sequence of xk like this, and we expect xk to converge towards the root. The root, that is the dominant eigenvalue. That's what we expect, right? And that xk, we can see it as rk, right? We see it as rk. But how is it related to rk? We will see. Okay, so power method, we have our matrix, and we have an initial vector. The initial vector can be arbitrary, or it can be given to you, or you can select it wisely in such a way that, because it's an iterative method, an iterative method works well if you remember, or if you don't remember or you don't know, stressing it again. Each time you have an iterative method, you need to find a good initial guess, because a wrong initial guess will take more time to converge. At the end of the day, it will converge, right? If you have a good method, a converging method, you end up converging. But it will take more time. If your initial guess is far away from the solution, it will take more time to reach convergence. That's why the good choice of your initial guess will accelerate. I mean, it will reduce the number of iterations towards convergence. I hope you understand the explanation. It's very important to understand these things. Very important. Okay, so we assume you have a good initial guess. Bam. Once you have an initial guess, you compute the x1, which is just the power method. That is, you multiply each time x k by a, and then you get ak plus 1. This is the iterative method, this one. Right. Okay. Now, once you get it, it's not yet finished, right? So that's why I was saying we will see how the xk is related to rk. Right. So these are our xk. You can see the xk are here. Now, what is our phi? Because remember, we need to find our phi and then take the ratio, right? To get an approximation of rk. Now, phi in our case will be the projection mapping. What is a projection? Let's say I have a vector in Rn. Let's say x is a vector. I will put the bar there to indicate that it's a vector. It has n component, x1, x2, up to xn. x1, x2, x3, up to xn. This is an element of Cn or Rn. Let me put Cn, but you understand that this can be Rn, right? Good. Now, the projection along maybe the ith component, I will call it PR for pro. This is PR comes from projection. Projection. Right? So from that, we just take this PR, we just say PR, projection. Now, sub I of xi of x, this vector x, will give us xi, right? In other words, if I is equal to 1, if I say PR1 of the vector x, it gives us x1. This is a linear mapping. It's a linear mapping, and you can prove it. So that's our projection. So phi, we will take phi to be that projection. It's a projection. Now, how are we going to project? Now, our projection will be along the entry, because we don't fix I a priori, right? We will look at the entries of xi or x, which is x to the, and find the entry with the largest magnitude. I say magnitude, I didn't say largest value. Largest magnitude, I forget about the sign. I look at the magnitude. If it's negative, I take it. If I take it, provided in magnitude is the largest. So I look the one with the largest magnitude, and then I project along that component. Like in this case, it's 2, right? I is equal to 2. Yeah, I have a problem here with the computer. It's a bit, it's busy executing. I don't know if you see that that disk. Oh, what is this? Okay. So I was saying, what was I saying again? So I was saying that here, I is equal to 2, because this is the entry with the largest magnitude. Once I obtain that, I project along the second component, meaning that I will take the ratio of that projection, x1 by x0. So for x1, when I project, I have 4. Now with x0, all the entries are 1. So if I project along, the second entry is still 1. So the first R will be 4, right? And R, remember, is an approximation of lambda 1. So that would be 4. So that's exactly what we do. And we repeat the process. We compute x2 by the same token. Now you see still 2. Okay, is 2. We do the same thing, so we project this along, we project along the second entry. So the numerator will be 11, and for the other vector, it will be 4. So we proceed, and you see it will be converging towards 2.5, right? Or 2.6 after that iteration. So that is the dominant. And if you take MATLAB and run, you see that the dominant eigenvalue will be 2.6, approximately. Okay, we'll stop here for today. I thank you so much for your kind attention, your patience. Yeah, it's already time. We have exceeded by 1 minute. We'll stop here for today. I hope this introductory lecture will encourage you to read more on the subject. What I will do after the class, I will upload it on here on the Microsoft Teams platform. Thank you. God bless you, and see you tomorrow. Bye-bye.